Don't hide your eyes from
All right, good afternoon, everybody. How's everybody doing today?
Woo!
Woo! All right, well, we are here today for lesson 35. We're going to be looking at hydraulic jumps. Our learning objectives for the day are as follows. First off, by the end of the class, you should be able to explain hydraulic jumps and practical applications, classify hydraulic jumps, calculate the upstream and downstream, which is also known as the sequent depth. It's the downstream depth downstream of a hydraulic jump. Be able to calculate the length of a hydraulic jump and calculate the energy lost in a hydraulic jump. This lesson is hugely important. If you had looked ahead, looking at what's coming on the final celebration of knowledge, problem 2 is going to be a hydraulic jump in a rectangular channel, and you will have to do all of these different pieces for that second problem on a celebration of knowledge that is going to be posted up on Canvas on Cinco de Mayo. It's going to be amazing. So that's where we're going. Let's start first looking at some hydraulic jump basics. So first off, what I want to show you is what a hydraulic jump actually looks like. So we've already seen portions of this video right here looking at supercritical and subcritical flow. And so what we're going to look at now is the actual hydraulic jump that forms right here. So you can see this hydraulic jump forming, and then as the water level back here gets deeper, it gets a little bit submerged. And so there's several different classifications for these hydraulic jumps that you're going to learn today. But anytime that you have white water like that occurring, you're generally going to have a hydraulic jump. Here's an example of a massive hydraulic jump that's created below a dam. It gives you an idea of some of the forces that you can see for a hydraulic jump. So I'm going to play that real quick to show you just how
hydraulic structures will be
massive
equipped
that
with some
is.
form of energy dissipator on the downstream end.
So you get an idea of those massive jumps there. Here are a couple of images of different hydraulic jumps and how they're classified, and you'll see those in your handout. And here's another example of a hydraulic jump occurring. Also here, you get an idea of this massive, massive waves, which is essentially what a hydraulic jump is. So looking at what those are. And I've actually got in the lesson handout for today, in the PowerPoint, so this is the same thing that you've got on Canvas. This is lesson 35. A couple of examples of what might be the largest hydraulic jumps in the world. So these are on the Itaipu Dam. This is on the border of Brazil and Paraguay. Before the Three Gorges Dam was built, this was one of the longest dams in the world. And you can see that when those spillways are running, you get a massive, massive jump.
Whoa.
Yeah, that's pretty gnarly. You don't want to go surfing down that. I would almost wager that by the time the water gets down that spillway, it's moving 70, 80 miles an hour. So if you got on there in like a raft or a surfboard or whatever, you'd probably get crushed in that hydraulic jump and die. So they are very, very turbulent, very destructive. And so when you design, you want to know exactly what the downstream depth is going to be, what the length is going to be. So looking at protecting that section of the channel with concrete. Some of the erosion that happened on the Oroville Dam a couple of years ago in California was due to hydraulic jumps that occurred in a natural earthen channel and just completely destroyed the emergency spillway on that dam. And there's another shot of Itaipu showing how big these hydraulic jumps can actually be. So let's take a look at hydraulic jumps, and when we're looking at open channel flow or design, So open channel flow and design, one of the main things that we're looking at doing with our hydraulic jumps, the main purpose is going to be to dissipate energy, right? That's why our energy equation fell apart when we talked about hydraulic jumps, is because there's such a turbulent structure, you're losing so much energy in those jumps that they can be very useful if you've got like a spillway. You've got water moving 60, 80 miles an hour down there. You want to dissipate that energy so it doesn't destroy everything downstream. So there are several other applications of hydraulic jumps, but that's kind of the main one. So we have a couple other applications. And those other applications are to prevent scouring or erosion, right? So you have that energy dissipation occurring somewhere where you have a hardened structure, so it doesn't destroy anything else. You can use it to aerate water. So you can use it to increase your actual oxygen level in the water, because they are a very turbulent structure. They create a lot of mixing. You can also use them to mix chemicals. Really crazy. So water treatment plants, paint manufacturers, anybody that's doing anything with a actual fluid, what they do is they'll create hydraulic jumps with some of the weirs and stuff that they've got in their facilities. And because it's such a turbulent action in the hydraulic jump, you can actually put in chemicals there, mix things.
That's cool.
Yeah, it's actually really, really cool. Or if you're mixing paint and you want a specific paint or a specific dye in a little channel, you have a hydraulic jump, that's right where you put it in. Farmers actually do this too for fertigation. It's kind of a fun word.
Fertigation.
Fertigation. It's fertilizing and irrigation at the same time. So
Ah.
if you've got some irrigation canal that leads to your field, you set it up so you got a little hydraulic jump in there, and that's where you drip your liquid fertilizer in, and it takes care of it, mixes it up real nice, and gets it out into your field. So there's a couple other ideas. The other thing you can do is to raise the downstream water level. It's another reason you're going to do a hydraulic jump, right? You saw in some of those examples, or right here, we're going to talk about this figure here in a second, you can see that this hydraulic jump, the downstream water level is much higher. And if you've got like a stream intake or some kind of channel that takes water off, you can get that jump to make that water at a higher level, to make it easier accessible. Turn off my email. It's probably going to tell me the university is closed anyway. So let's not think about that. Okay. So the question is, how are we going to classify our hydraulic jumps? And generally, they're classified by the upstream Froude number. Right? So do you all know how to calculate your Froude number?
D over square root of 2G.
Yeah, right. Our Froude number, excellent. It's going to be V over the square root of GD. So you can calculate out what your Froude number is quite easily. And the way that they are classified is this figure 15.2. This is in your handout from Chow. So Chow is the one that wrote that, essentially the Bible of open channel hydraulics. Last time it was issued was 1959. That basically tells you, based on that upstream Froude number, what those classifications are. I highly, highly recommend that you put these classification numbers into your cheat sheet for the final celebration of knowledge, because it will ask you to classify a jump based on what you're looking at. So generally, these jumps, if you have a weak or undulate jump, your Froude number is going to be 1 to 1.7. It's an undulate jump. A weak jump is 1.7 to 2.5 for the Froude number coming in. An oscillating jump, so that's something that moves around back and forth. It's not always in the same place. That's a Froude number of 2.5 to 4.5. A steady jump is a Froude number of 4.5 to 9. And a strong jump is a fruit number above 9. So generally when you're designing, so for design, you want at least a fruit number of that's greater than or equal to 4.5, because that jump won't move around. It'll be nice and stable. It'll dissipate a lot of energy, and it'll be predictable. Like this one's kind of the worst. It's an oscillating one. You have no idea where it's going to be. It could be over here, then it could be over here. And guess what you have to do as a design engineer if you're one of those jumps? You got to line this whole entire area with concrete, which is going to cost you a bunch of money. You're going to go out of business. Not really the way you want to go. So it gives you an idea on how those jumps are actually classified. To do more of this classification, you've got table 4.8 in your textbook. That's on page 141. If you want to look at that, that's where you can find it. So let's take a look at how to actually do the analysis for this. What does it look like? So let's have a channel. And hydraulic jumps are generally in flat channels. Usually don't want them occurring on a steep apron. So for analysis purposes, right, you could have like a really steep part of a channel coming down here, but then you want your hydraulic jump on that portion of the channel. And what you're gonna have is you're gonna have some flow level, and then you're gonna have crazy turbulent stretch. You're gonna have your Y1, it's your upstream depth, and your Y2, which is gonna be your downstream. So this is what's gonna be called your downstream, or it's often called the sequent depth. And this is going to be your upstream depth. Okay, and the main key error that I often see here is this is where you're going to calculate your fruit number to classify your jump. You got to calculate it at that shallow jump. So if you do not have a really shallow supercritical flow, you cannot have a hydraulic jump occur. So this is always supercritical, right? The fruit number has to be greater than 1. And this part over here, this is always going to be subcritical, which means the fruit number has to be less than 1 in those cases. Okay? Now, if we're looking at these cross sections, so this is cross section 1, this is cross section 2, how are we going to actually analyze this? Can we use our energy equation? What do you think? D'Artagnan, can we use our energy equation?
Oh yeah. Why wouldn't we be able to?
To use our energy equation?
What are we trying to solve for?
We're trying to solve for this jump. We're trying to figure out like energy dissipation, any of the other things. Can we use our energy equation for that? Think back. Think back to lesson 33 and 34. Can we use that energy equation?
Was there an assumption in there that makes it so we can't?
There was, right? That was one of the main reasons we were using momentum, is because you have so much energy lost in the hydraulic jump that the energy equation breaks down.
Right.
Yeah. So glad you remember that, D'Artagnan. That's perfect. Okay, so because we can't use energy, what we're going to have to use is we're going to have to say that force 1 is going to be equal to force 2 at those sections. And we're going to make a couple of assumptions. And those are going to be that we're going to neglect friction, and we're going to assume that there's no obstructions. Right? You definitely don't want to put like a broad-crested weir in the middle of a hydraulic jump. It's not going to be a good situation. You might do that if you were a student at an unnamed university north of here. but not here. All right, so let's continue on and look at what we're actually going to be using. And what we're going to be using is our momentum equation. So if those forces are equal, this force and that force, let's write it out. So it's going to be Q squared G A1 plus A1 Y bar 1. It's going to have to be equal to Q squared G A2 plus A2 Y bar 2. This is equation 4.135 on page 140. So that gives you an idea, right? This is just a recap of what we had in the previous lesson, looking at that momentum equation. Now, the beauty of this is we can actually break this down to something a little simpler. So if we're looking for a hydraulic jump in a rectangular channel, which is going to be the question on the final celebration knowledge. I'm not going to ask you to do a trapezoidal channel on the celebration because most of the time on the FE you're going to have to do a hydraulic jump in a rectangular channel. Now, the next lesson we're going to be doing a hydraulic jump in a trapezoidal channel. Why might I be doing that to you?
Happens in real life.
It happens in real life, and I totally got asked to do a hydraulic jump in a trapezoidal channel for my PE.
Oh.
So just to prepare you for that, the hydraulic section of the PE is generally going to include probably a trapezoidal one for the PE, and the FE is going to include a rectangular one. So that's another reason why this is so important. So if you're in a rectangular channel, there's actually a great relationship to calculate out what depth you're going to be at. So the relationship looks like this, is that Y2 over Y1, so this is your downstream or sequent depth divided by your upstream depth from the jump. It's going to be equal to 1/2 the square root of 1 plus 8 times the Froude number at 1 squared minus 1. So if you know everything going into that jump, if you know the flow depth, if you know the flow rate, channel, velocity, all that stuff, can you get your Froude number? Yes, right? You know how to do that. Multiply it by 8, add 1, take the square root of that, subtract 1, multiply it by half. Then if you know Y1, you're instantly going to be able to get your sequent depth for a rectangular channel. So this is a really, really nice simple equation to calculate that out. So this is equation 4.140, and it's on page 140 as well. Now, this is where things get a little crazy. Right? And I had hinted at we were going to prepare you for the PE. Well, here we go. We're going beyond just the FE. So what happens if you're not in a rectangular channel? What can you do? What's A? And what's Y bar for those calculations? Okay. Actually, it's not too bad. So if you're in the trapezoidal channel or a triangular channel, what that might look like. So if you're in a trapezoidal channel, you're going to have your bottom width B, you're going to have your side slopes 1 to Z, and you're going to have your water level, and you're going to have some flow depth. So the great thing for trapezoidal channel, if you relate that, it's going to be A is equal to B plus ZY times Y. That's not so bad. You can easily plug that into here and get your forces. Same thing for a Y bar, right? You can easily get that. So this piece usually is what you're plugging into here, and this second part is the A and the Y bar together. And what that looks like is BY squared over 2 plus ZY cubed over 3. So now you're ready. You could totally calculate what's happening in a hydraulic jump for a trapezoidal channel for your PE. The one trick that I want you to be aware of, right, is using your solvers and your calculators to do this, because that's how you will set this up. You'll be solving for Y in this, right? So you'll probably be having the actual number for this part. You'll know what the flow depth is, and therefore you can calculate that. When you plug it in your solver is going to spit out two different answers. It's going to spit out the exact same answer that you have for your Y over here. What you have to do is you have to tell it to solve from a higher bound. So that's the same kind of thing we talked about for looking at your solutions to like green amp and all those other equations. Just type in before you hit shift solve. When you hit shift solve, type in like 2000 and hit enter, and it'll solve it down, and it'll give you that higher sequent depth downstream. Now for a triangular channel, this actually looks a little simpler, which is nice. So if you have your triangular channel, you have your water level, you've got your Y, and you've got your 1 to Z. What that'll look like is your area for trapezoidal channel is simply going to be ZY squared, and your AY bar is going to be ZY cubed over 3. So it's actually the same as this minus that rectangular portion in the middle. So that kind of makes it simpler. You don't always have a trapezoidal channel or triangular channel. It might get thrown in there as a kind of a trick question. So just be aware, any of that with simple geometric relationships you could actually solve without having any of this in there anyway. Now let's look at energy loss. How is energy loss calculated in a hydraulic jump? So if you didn't know any better and only knew Y1, Y2 in flow rate, you could easily do delta E is going to be E1 minus E2, right? So you can calculate that using the energy equation once you've figured out what the downstream depth, what the downstream velocities are. So that's an easy way to do it. Now, if you're in a rectangular channel only, which we are going to be for this class, especially for the final celebration, if you're in a rectangular channel only, the following equation can be used. So that delta E is going to be Y2 minus Y1 cubed over 4 times Y1, Y2. A couple other things here that you need to calculate. You might need to calculate relative loss. So if you're looking at how much energy is actually lost, that equation is just going to be delta E, so the change in energy, the energy that's lost, over your beginning energy E1. A couple other things that might be important to you could be height of the jump. So height of the jump, the way to calculate that is going to be height of the jump over E1 is going to be equal to Y2 over E1 minus Y1 over E2. And I'm going to move this equation, the next one over here, onto this page, or onto this board, excuse me. If you're looking at the height of a jump in a rectangular only, so this is height of the jump in a rectangular channel, you're going to get a relationship between height of the jump related to E1 is going to be the square root of 1 plus 8 times the fruit number at 1 squared minus 3 divided by the fruit number at 1 squared plus 2. And what you can do there as well, let me get the chow figure up because we're going to have to be looking at that here in a second anyway. Chow figure, what it shows you is this is the figure for length, and then the figure, must have gone too far, the figure for height of the jump is chow figure 15.2. We're going to move on to looking at, pull this figure up right now so we're ready to go. Is looking at the actual length of the jump. Why might the length of the jump be important? Chris, let's ask Chris Pike. Why would the length of the jump be important?
When you're designing your spillway, knowing how far it's going to be having an impact.
Bingo! Great answer, Chris. That's exactly what you're going to be looking at, is how long that length of the spillway is. How much concrete are you going to have to pour? How are you going to have to design it? So, the beauty of this chow figure, so that's what you're going to be using, is chow figure. This is 15.4. and that's given in the handout, is you take your fruit number at 1 and you relate it to an L over Y2, okay? Where your L is equal to your length. So let's say we've calculated our fruit number for one of these jumps to be 7. Right, so we've got 7 at our jump. It's a strong, steady jump. It's a well-designed jump. We go up to here, get this ratio. So you come over here, and this ratio would be like 6 point. So it'd be like 6.1, something like that. Not quite 6.2, so maybe 6.15 is what we'd say that ratio is. And so then 6.15 would go here. You relate it to L over Y2. If you have Y2, you multiply it through and you would get that. So in our example, let's say that gave us a ratio of 6.15. Let's say our downstream depth of this jump was 10. So we would take 10, multiply it by 6.125, and we'd get that the length of our jump is 61.5 feet. How that math would work out for calculating the length of our hydraulic jump. There are other equations to figure out the lengths of jumps if things get really complicated. If you're not in a rectangle, so if you're not in a rectangular channel, you can say that L over Y1 is going to be 220 times the hyperbolic tangent of your fruit number 1 minus 1 over 22. So if you don't, you're doing this for a trapezoidal channel, that will give you a way to calculate out what your hydraulic jump length is. All right, so let's take a look real quick at our lesson 35 worksheet. I'm going to pull it up on the screen so we can all look at it together and I can give you some pointers. Obviously, if this was not our coronavirus sequestration of students, Jake and I would much rather be doing all these worksheets with you guys, but the way we have to do it is this. So here we go. This is worksheet 34A. In that worksheet, we calculated the thrust on this sluice gate. We calculated the force on this to be about 550,000 newtons. So, whoa, right? Crazy force. Now we're going to look at what's happening downstream of that same gate. So what we're going to do is, just to put this in perspective and make sure you're doing the right math, I kind of want to set you up for success, and this is how we're going to do that. So basically, this 10 doesn't matter, right? We're looking at this jump. This is where the jump is. We're trying to figure out what's happening here. How much energy is being dissipated, what's happening. And luckily, we're in a rectangular channel. It's 5 meters wide. So we want to get the flow depth downstream of the jump. We want to get the head loss in the jump, the type of jump, and the length of the jump. So first off, this is 2 meters deep, 5 meters wide, and our flow rate is 150 meters per second. Can we get velocity?
Mm-hmm.
Yeah, can you get your fruit number?
Yep.
Yep, if you got your fruit number, can you use the fruit number equation to calculate for a rectangular jump what the downstream depth is going to be? That one's no longer up on the board, it got erased, but it's one of the first equations in there. So that's how you get Y2. Once you've got Y2, can you use this equation here for the energy? I can pull this over. Can you use this equation to figure out what your delta E is going to be?
Oh yeah.
Oh yeah, right? So you can easily do that. Once you've got that figured out, you can easily get the type of jump that's going to be classified based off figure 15.2 from Chow as either undulating, oscillating, weak, steady, strong, based on that fruit number. And then the last piece, the length of the jump, right? You're going to be able to get that from figure 15.4 in Chow, looking at L over Y2 once you have your Y2 calculated. So that is how you go about successfully calculating everything for those hydraulic jumps. Your answer should look something like this. When you calculate it out, your V1 should be 15 meters a second. You get your fruit number to be 3.38. Your Y2 should be 8.63 meters, which gives you a head loss of about 4.22 meters. The type of that jump, when you look at Chow's figure, tells you that it's an oscillating jump, which means, oh crap, you got to redesign that thing because it's going to be bouncing around and causing problems. And then you get your length to be 47.5 meters in terms of the length of that apron that you're going to have to design. So let's take a look. So hopefully after completing that worksheet, you should be able to do all the learning objectives. Can you explain hydraulic jumps and practical applications of them?
Yes.
Excellent. Can you classify hydraulic jumps?
For sure.
What are they classified off of?
The fruit number above stream.
Yes.
Upstream.
Excellent. Can you calculate the upstream and downstream or sequent depths of hydraulic jumps?
Yes.
Yes. Can you calculate the length of a hydraulic jump?
Oh yeah,
I would think so. And then finally, calculate the energy lost in a hydraulic jump.
we can get there.
I think you can too. Thank you so much for tuning in today. I'll be giving you a quick review. Just to keep things straight, lesson 36 does not exist. Lesson 36 was going to be the demo design day. So the next lesson in the sequence is going to be lesson 37, and that's going to be us calculating hydraulic jumps in a trapezoidal channel, and that will be coming at you in 2 days' time. Have yourselves a wonderful rest of the afternoon, and looking forward to hydraulic jumps and trapezoidal channels, lesson 37.